Welcome to this explainer. Today, we are going to peel back the curtain and demystify the spectacular magic trick that is artificial intelligence. You know, if you've been using tools that generate text or create those stunning, sometimes weirdly accurate images, you know exactly how seamless it feels. But today, we're going to look right past that illusion and see the gears turning underneath.
When you type a prompt and get an incredibly nuanced answer back, it really feels like there's a sentient mind sitting on the other side. But Steve's AI lab hit the nail on the head with a profound realization. It is not magic at all. It is math. It's just a massive, brilliantly structured layering of ones and zeros, additions and multiplications.
Section 1, not magic, just math. Deconstructing the AI brain.
So we are going to start by looking at the fundamental machinery powering every modern AI system. The real brain of AI is just a spectacular layer cake of mathematical operations. A neural network is inspired by the biological neurons in our own heads. Picture a giant grid of nodes. Data comes in through an input layer, travels through multiple intermediate hidden layers, and finally pops out at the output layer. And at every single node, it receives a numerical signal, multiplies it by a specific weight, adds a little bias, and passes it through an activation function to decide what moves forward. It is literally billions of tiny math problems happening all at the exact same time.
As data flows through this model, it's continuously updating itself through a mathematical error correction process called backpropagation. Honestly, think of it like practicing darts. You throw a dart, see how far you are from the bullseye, and you adjust your arm just a little bit for the next throw. When an AI produces an output, it compares its answer to the correct one and calculates exactly how wrong it was. Then, it sends that error backward through the network, adjusting all those tiny weights so it does a better job the next time around. It literally learns from its mistakes, optimizing itself cycle after cycle.
Section 2, the language of machines. Turning words into numbers.
Now that we understand the underlying math, we need to see how machines actually read human language. Because here's the catch. Neural networks absolutely cannot read letters or words. They only understand numbers. So they rely on a process called tokenization to translate our words into a math-friendly format. Before a model can summarize a document or answer your question, a tokenizer has to break the raw text down into smaller, manageable chunks, called tokens, and assign a unique numerical ID to every single one.
Nebius has this absolutely perfect analogy for this. Think of tokenization as turning language into Lego blocks. Just like you can build an infinite number of spaceships or castles from a finite set of Lego pieces, an AI uses a predefined vocabulary of numerical tokens to interpret and generate the vast, beautifully complex range of human language.
It's a surprisingly simple three-step workflow. This is the invisible layer that transforms our messy human language into machine-readable data. Let's say your input is Nebius is the best. The tokenizer takes that string, splits it up, and then maps those pieces to an ID based on its vocabulary. So Nebius might become the number 5001. Is becomes 40, and so on. Natural language goes in, and machine-readable numbers come out.
Of course, engineers had to figure out the best way to actually chop up these blocks. If you just tokenize whole words, your vocabulary gets way too big, and the AI totally fails on misspellings. But if you tokenize single characters, the sequences become extremely long and computationally heavy. So modern systems rely heavily on subword tokenization. It's the Goldilocks zone. It breaks things into meaningful fragments like un and able, efficiently handling everything from unusual spellings to complex code snippets. This is the exact method powering major models like GPT today.
Section 3, 3 phases of training. Building a helpful assistant.
Okay, so we have the neural network and we have the tokenized data, but how do we actually train it to hold a conversation with us? Well, according to Snorkel AI, it takes a highly structured 3-phase training stack to turn a raw text predictor into a genuinely helpful AI assistant. First up is self-supervised learning, which feeds the model vast amounts of raw data to teach it to predict missing words, like knowing the word night probably follows a flash flood watch will be in effect all. Second is supervised learning, also known as instruction tuning. This step teaches the model to actually follow explicit commands rather than just randomly auto-completing sentences.
The final phase, reinforcement learning, is super fascinating because it uses human annotations to mathematically reward the AI for being safe, concise, and helpful. Actual data scientists grade the model's outputs, and this human feedback trains a separate reward model to score the AI. This is exactly how the AI learns fuzzy human concepts, like how to politely decline a dangerous request or how to adopt a really specific tone of voice. It's why your AI assistant feels so polite and helpful instead of just spitting out random internet facts. It completely aligns the mathematical output with our human expectations.
Section 4. The Art of Diffusion. Painting with Noise.
We've mastered text, so let's pivot to the visual side of AI and explore the spectacular illusions of image generation. If you've used Midjourney or DALL-E, you are interacting with a diffusion model. And it sounds completely backward, but training an AI to draw starts with teaching it how to systematically destroy an image using noise. During forward diffusion, the system takes a perfectly clear image and incrementally adds random Gaussian noise to it over many steps, ultimately degrading it until it looks like a TV screen of pure static.
So if forward diffusion just completely wrecks the data, leaving absolutely nothing but visual static, you have to ask the obvious question. How does reverse diffusion actually work? How on earth does the machine pull a brand new, highly detailed masterpiece out of pure randomness? This right here is the core magic trick of visual AI.
All right, let's dive right into this. The neural network is mathematically trained to estimate the noise at each step and subtract it, literally sculpting an image out of randomness. By studying exactly how images were destroyed during training, the network learns to predict those noise patterns. So at inference time, we start with pure static. The model predicts the noise, removes a little bit, predicts again, removes a little more, and traces its way back, guided by your text prompt, to reveal a breathtaking image that has literally never existed before.
This step-by-step denoising is exactly why diffusion has largely replaced older models like GANs. Older GANs were notoriously prone to something called mode collapse, where they would aggressively generate the same limited images over and over, usually featuring people with terrifying mangled hands. Diffusion models, on the other hand, slowly map a stable path from static to structure, avoiding those crashes and creating a vastly wider, incredibly realistic range of imagery.
Section 5. From Lab to Real World. The Future of Applied Math.
These diffusion processes and large language models require billions of calculations. So how do we take these massive, computationally heavy illusions and squeeze them into the smartphone in your pocket? Well, through real-world optimization. By compressing the math and teaching student models to skip steps, engineers can make these systems run instantly on everyday devices. Quantization literally compresses the neural network, reducing its file size while keeping the accuracy intact. And techniques like progressive distillation take a massive teacher model and train a smaller student model to achieve in one step what used to take the teacher 2 steps. That is why an image generation process that used to take hours in a giant server farm can now happen in mere seconds right on your phone.
So, now that you know the illusionist secrets, that there is no sentient brain in there, just billions of mathematical weights, clever tokenization of language, and the precise subtraction of static noise, I'll leave you with this to ponder. If pure applied mathematics can compose beautiful poetry and paint masterpieces, what new frontiers of human ingenuity does this open up for us to explore next? Thank you so much for joining me on this explainer, and remember to always keep questioning the magic.